Hi, my name's Dan, and this video is one in quite a long series of videos charting the progress of simulating a fairly simple 4-bit CPU in some digital simulation software called DigitalWorks. And I'm starting from basic logic gates and going all the way through to a working programmable CPU. So there's a roadmap of where I'm going in the description down below. And there's also a link to the software that I'm using to simulate, which is called DigitalWorks. And I'm doing simulation because it's cheaper, because I don't need to buy hardware and solder it together, and because it's actually more visual as well, so it's easier to follow what's going on. And where we're up to is that within the larger scheme, there's a shorter set of videos which are about creating the ALU, which is the arithmetic part of this circuit. And we've got to the point where we've created some specific parts for that, and it's time to put it all together. So the first video in this series discussed what we were going to need. We've been following that through in the next couple of videos, but we're going to kind of reiterate. I'm going to drag a number of things in, and then we're going to wire them up. So we started out with the actual mathematical bit, which is the add XOR, so this can do either adding or XORing. And then we've got another bit, which is the B choice, so this chooses what actually our second parameter is going to be fed into our add XOR, in fact, to our B. This is why I call it B choice. So it might take it in from the B input. It might be an inverted version of that, or it might be hardwired zeros or ones. And that's controlled using the control number coming in here. The other numbers that we've got is that we've got a control coming into the add XOR, and we've got a C in. And I'll put them in the right order as we get to them. We've also got an output here, and we've got a C out and a Z. And I have a general principle that I'm following through all this simulation set, which is that when we have an output, if it seems reasonable, I'm going to turn that, connect a register to the output to make that a bus-enabled output. I'm not going to do that with inputs because there are significant times when you want to directly connect an input to an output, and so you end up doubling up on buses. So I don't want that. So I've used this general principle. If it's an output, if it's suitable, I'm going to make it bus ready, and so that then the components as a whole can connect to the bus, and they all look like they're able to talk to each other, which is good because they can. So that was a kind of preamble for the fact that I need a register here. So I'm going to have a 4-bit register to store my outputs, which is going to go there. I will have bus connection here. But I'm also going to use another register for storing the flags. We've only got 2 flags, which are the Z and the C out. I am going to use the 4-bit register just out of laziness, to be honest. I probably could be using a 2-bit register, and if I could be bothered to kind of sit down and create one, then that would be fine. It's a little bit wasteful using a 4-bit register here. If you were doing this in proper hardware for production purposes, you would bring down your number of gates as much as possible. So these registers were designed to be quite widely usable, so not everything is going to be wired up in the registers. So let's start to do some wiring. There's not lots of wiring here, and it's all different, so I'm not going to fast forward this wiring process. I'm going to talk through it as I do it. So I'm going to wire up the output from the B choice to the B input on the add XOR. I'm going to give us an A input, put that close up to the box where we're going to want it. I will add an annotation on that so that I'm careful to know where I'm going. Okay. And we need to connect up the B input similarly. So just do 4 input tags or 4 tags there. Right, and the output is going to go into the data input on this register. So when we want to actually collect the output, we need to use the data read. And similarly for the flags, we're going to connect that up to the data, and there's no reason not to just use the bottom two. And I will need to remember that that is the Z and that is the C out. So that will connect to the bus, and that's a bus ready output. The two flags here actually are going to connect. I'm going to bring out the values rather than do it on the bus, and that's because I know what these are going to be used for later, and they're going to be. They don't need to be on a bus. They just need to be remembered and used hardwired. Right. So the data read. Let's talk about that. No, let's come back to that. Let's do the control. So we're going to have a 4-bit number, which is our operation, which is telling the ALU which particular things it's going to do. And we had a discussion in the first video in this series about how we can make that happen, and we've been fairly clever about the use of this. In that, let's annotate that now whilst we're ready for it. So we're going to call this opcode, which is the general term used for this. 3 to 0. I need to make it slightly higher. So I'm going to use the bottom two are going to connect to the B choice. So 0 and 1 gives our B choice. They could be wired in a different order, but I just happen to know that this order worked when I did it before. The next one I'm going to connect to the C in for the add XOR. So that's our +1. Then the final one is going to be used to choose whether we're doing add or XOR. So that's the control for the add or XOR. And that forms our opcode. So the most significant bit, 1, tells it whether we're using add or XOR. The next significant bit here tells us if we're using a carry in or not. So if we want to add 1. And then the bottom two give us our B choice. So 0, 0, 0, 0 gives zeros coming through the B choice, and it's going to be an add, which is 0, and so and no C in, which is 0. So it's basically add 0 is 0, 0, 0, 0. We're actually not going to use that opcode as one for the ALU, because as we had in the discussion in the first video, only some of these are going to be useful, but we'll deal with that externally and separately. Right. Let's wire up the bus output whilst we're dealing with such things. So that's going to be a set of pins that are going to be able to connect to the bus, and so the output for the ALU will go to the bus. And because of that, whenever you have bus connection, you need to also put in the bus read. Actually, we're going to use bus read? No, we're not. Output enable, because it doesn't need to read from the bus into the output. We only ever want the output to come from the ALU itself. So we're wiring up the output enable, which is necessary, but the bus read isn't necessary. I'm nearly there. I was going to talk about the data read. So what I'm going to do is I'm going to connect up the data read for both of these registers. And there's a little bit of trickiness going on here. which is that timing has not really been paid attention to yet. So let's talk about that. So when we give it an opcode, it sets itself up uh, in the B choice and in the add XOR so that the output is what we want. But we want to trigger that actually being stored in the output registers. And the way to do that is to use data read. What we're going to call this input isn't going to be data read, it's going to be execute. Um, and what's kind of crazily is happening is that actually the hardware is going to do quite a bit of processing, but it's only going to be when we hit data read that it's actually going to capture the output for it. And we just need to make sure that the opcode is there before we do the data read, or actually, more precisely, we take the data read low once the circuitry has had a chance to manage to settle in with the opcode and everything has been set up as it should be. So that's how the timing works. And typically this will come in as a clock pulse in the enable. So let's do some labeling of stuff. We've got our B input, so that's B3 to 0. We've got our A input, which is down here, A3 to 0. We've got our bus, and we'll put that on its side so that it's bus 3 to 0. Again, I just find that getting these labelings done in this particular way helps me to keep things straight. We're not connecting anything up to the value there. We are connecting up to these, so we're going to use, now let me check which one's which. This one's C out. And the other one is Z. Well, we might as well have these labelled so that we're not having any confusion here. I'm not thinking of this as being a binary number. I'm thinking of this as being two separate lines that are flagging the two separate conditions that come through. Right, so visual checking. First of all, opcodes. Bottom two go to the B choice. We've got them lined so 0 to 0 and 1 to 1. Next one is the C in, and then the top one is the control. We've got A coming in, we've got B coming through the B choice and then in, and then the output coming down to the register. The register is triggered with this execute. So let's label that. And we've also got these two outputs, and then we've got output enable for our bus connection. And we don't need output enable on the flags register because that's not a thing. We're not going to connect it to the bus. I'm just going to add another couple of labels in so that we know that this is the output on. It tends to be called ALUX or ALUY as a register. I'm calling it ALUX. And this one is flags, sometimes known as status or status flags. Okay. Right, so time to hook this up to a template. I hope you find that you've followed this through and you've understood what's going on here. It's underneath there's quite a lot of things happening, but we've done it in bit by bit and broken it down into various sections, and this should be an understandable piece of simulation. Anyway, let's go to the template. So first of all, we need to change this and make sure it has it says ALU. Right, and we are going to need it to be bigger. And do we want it to be taller? What we're going to do is, like we've done with other elements, is that I'm going to make the bus connection on the left-hand side so that this is a standard thing for all my components that are bus ready, so that I can just line them up one above the other with a bus. Have I got enough space to get 4 lines on here? Only if I shrink it. I'll shrink the pins or expand the box. Let's try shrinking the pins and see how that goes. Not shrinking the pins, making them close together. Has that worked? I'm going to expand the box a little bit. Right. Okay. So we're going to need A and B inputs. That's already saying it says B on it, so let's put it to the right, which is fairly normal for B. Doesn't have to be, but these conventions are sometimes useful to follow. Just kind of keeps it visually in your head straight. We're going to need an opcode, and what else? We need the flags out. So where should we do what? Let's make it longer a bit and put the opcode in the top. So maybe not traditional, but I don't see why not. Might want plenty of space at the top to get stuff in. Opcode 3, 0. There we go. What else are we going to want? We need our enable, so our execute, and then we want our flags. And I'm going to put the flags at the bottom, kind of bottom right, down here. And let's check if I'm going to do anything else. So that's the, I keep calling it enable, it's execute is what I want to actually call it. That's clicking on the wrong bits. Execute. We've got our opcode, we've got our B, we've got our A, we've got our bus connection. We haven't labelled the bus connection yet. Output enable. So I'm going to put output enable down this end near the bus output, just to kind of make sure it feels associated, but not quite that close. And I'm going to label it OE for output enable. So I'm going to move that further over. So one of the reasons that I'm kind of thinking about this and making decisions is that I did a test run through making this thing, which is kind of a fairly obvious thing to do. But I wasn't happy with the layouts with that, and I haven't done a separate run through with a change layout, so I'm making the layout somewhat up as I go along. So we'll be able to appraise this later and see whether we've done a good job of this or not. And obviously, if you want to lay it out differently, that's entirely up to you. And it doesn't look like a V shape, like the standard kind of diagram for an ALU is. Now let's make sure we get these the right sort of way around. So C out. I seem to be inconsistent with whether I'm using a hyphen and how my capitalization is going with C out. And I guess the question is, does it matter? Maybe it would be better to be consistent. Don't think I need that one. So I'm just doing another visual check to check that I've got the right number of inputs and outputs. I've got C out and Z, I've got output enable, I've got execute, I've got bus, I've got an opcode, and I've got B and A inputs. Okay. So let's do the wiring up. Hopefully it's clear what's going to be wired up to what in this, so it should be safe for me to play some music at you. Right, that should be that, and get to the point where we can save it and call it ALU. This is quite an exciting point, actually, because hopefully we now have a working ALU, which is quite a major component in the CPU. It's actually, this is the mathematical bit. So let's get to testing it. ALU, let's drag it in. So once again, there's a reasonable amount of stuff to wire up here. I'm going to create a bus that I can see. I'm only using the bus for output in this case, not for input into the ALU. So I don't need to create a separate input for the buses, but it'd be nice to see what the content of the bus is. So I'll make it look like a bus. And I'll wire up inputs and outputs so we can see it. But again, we'll go back to the music because there's not really a lot to say whilst I wire things up. Right, we're ready to get going. I've started simulation, and we're going to have to do some thinking about how we're going to test this, how we're going to do so effectively. So let's start with, we have to try and remember what the different things are that we're meant to be able to do. So obviously we'll need to be able to add two things together. So let's put in 10 and 2, and this should give us 12 output. At the moment, it's settled on a C out, does it? We maybe should have a clear as well. That would be quite a useful thing to add to the ALU, just to clear the output. Let's just do execute. Actually, execute works as a clear when nothing else is connected. Well, you might want a separate clear. We'll think about that later and adapt it if we do. So the opcodes, the bottom two here tell us our B choice. That one's C in, and this one's the whether we're adding or doing XOR. So we should be adding, because that's 0. Our B choice, this should not be figuring, it should be 0. So when we execute, as we did there, that should mean that actually now it's storing 10. Let's see what happens. Yes, I love it when we predict something fairly complex like this. Let's try and add A and B together. So that was add is correct. We don't want C in, but we want that to be high because that's the thing that says actually use B. And execute. It's not giving us a Z or a C out, and our enable this should go to 12, and it has. So that's good. What else do we want to do? We want to check increments and decrements. So how do we do that off the top of my head? So A, and for increment, we'll just add 1. So we're going to have C in is going to be 1. So we use that. but we're going to use 0 for the B. So an increment from 10 should be 11. Let's execute. And then output a label. So this should be 1001. No, I was wrong. It should be 1010, and that is in fact 11. That's correct. I was thinking of decrement. So decrement, if you remember, we're going to do this by adding 1111 to whatever we've got. So again, we're adding, and we don't want C in to be flagged, but we want to use the ones, which is that one there. So let's execute. This should be 1010. You notice the C out has been flagged here. Sorry, 1001. I am in my head. I'm doing it right, even if I'm saying it wrong. We also wanted to compare, so that's one that does with the XOR. So let's do a comparison between A and B. We want to be choosing B by doing that. We'll need to try subtraction as well. So the compare needs to have that bit switched so it does in comparison. And we should, when we execute, we should get a Z of 0 and an output of 0, 0, 0, 0. So execute. The Z has, sorry, not a Z of 0, a flag saying it is 0. But the output should be all zeros. Yes, that's right. Let's try comparing things that aren't the same. That Z should now go down, and this should give us the XOR between the two. But it's actually that Z flag that we'd be interested in if we're doing a comparison. So yes, it has gone there, and just check that. Yes, that gives us the one. Right, finally, well, I don't know if it is finally. I think I'm checking everything. I'm going to do a subtraction. So I'm going to do 10 minus 3. Sorry, 10 minus 7. So let's put 7 at the B. And what to not do. Yeah, we need to check inverse as well. So this isn't finally. So 10, 7. We want the inverse of B, and we want to add C in to make that work, and it's an add. Right, so this will probably overflow. It does. And what's 10 minus 7? It should be 3. 3, hurrah! Finally, inverse. So an inverse is done by XORing with ones. And so ones is done using that. And we don't want to see in. So the XOR of 1010 should be 0101. So it'd be the XORing A. Execute. And let's check the output. 0101. Everything seemed to happen as I was predicting it, which I hope means that our ALU is working. As you can see, it's quite complex trying to work out what exactly you're doing in terms of testing here. So I hope you managed to follow at least some of that, and you managed to devise your own tests to check that things are going okay in this. And the way we're going to take it forwards is that this is then going to be surrounded with several other bits of gubbins and registers and stuff to make a working CPU. But that's it from me for now. Actually, no, I'm back. You thought that was it, that you'd finished with me. Not quite. I've done a quick check, and previously I did have a clear tag on my ALU, so I'm going to add that quickly just to show you how to do that. So this is the ability at maybe at the beginning or of running the simulation or any other point is to actually clear the what's being held in these two registers. So I'm just going to add an annotation. Oh, that should be 10 points. Don't need to retype it, I just need to change the size. Okay, and this is connected up to the clear for both of those registers. So it's just going to set us down to a full zeros inside there. So once again, of course, this needs to go into the template, and I'm going to stick an extra pin just beneath the executes, which I'm going to call clear. And in fact, to give that text a little bit of space, I'm just going to slide those up a little bit. That version of the annotation. It's still got the word clear in it, which is quite useful. And then, of course, I need to wire that up. What am I doing? Yes, template editor and clear. Okay. And I probably should go through the whole process of wiring all that up again and testing it with the clear. But in this particular occasion, I'm pretty confident that just adding one clear is going to be fine. So I'm not going to bore you with that process at this point. So genuinely, I hope that's it from me for now.